Welcome to Ideas in Action, the official University of Southern California podcast. Shows are webcast live on Facebook from Studio 1A in the USC Annenberg School for Communication and Journalism.
Where do we stand today in stem cell research and the things that have flown from it?
Yeah, well, there's many answers to that at many levels. In California, the CIRM initiative has had an enormous impact at many universities in the growth of stem cell research and the application of novel stem cell therapies. I'm a lucky recipient of that because it brought me here from Harvard about 7 years ago. So if we cast our minds back about 50 years ago, that was when the first clinical application of stem cells happened. It was in the bone marrow transplants that most of the public are familiar with, and that saved many hundreds of thousands of lives.
And that would be at a time when the use of stem cells was coming from the hematopoietic stem cells that are in the bone marrow,
right,
that generate blood and so forth. And so if a person had a cancer and you could use radiation or chemicals to obliterate their cancer and then give them a transplant from someone who was healthy, they could generate cells that were free of that cancer. That was the hope. And many hundreds of thousands of people were saved that way.
So that was the use of stem cells that are present in our bodies that every day are involved in renewing the cell types of our different organ systems. And this happens for the blood, it happens for our skin, it happens for our gut. But not all of our body systems, our heart, our kidneys, for example, have stem cells. So a huge advance that's happened in the last 10 years is the approach to generate stem cells from patients or from basically anybody that have the properties and potential to give rise to any cell type in our body systems.
And that work is more recent than the bone marrow transplants you talk about. Because it was just over 20 years ago that two sets of scientists, one in Wisconsin led by Jamie Thompson and one at Johns Hopkins University led by John Gerhardt, developed a means of creating lines of embryonic stem cells. How was that different, Andy, from what had existed before?
Yes, so in the late 90s, early 2000s, those groups initially and then several other groups used a small number of donated human embryos to generate these cell lines from an early embryo. And as you'll realize, the cells in an early embryo, their destiny is to generate all the cell types of our body system later on, so they have that property. And so if you know how those cells do this in normal life, in normal developmental life, then you can unleash those cells to generate any cell type.
So that work, unlike the attempts to cure cancer with bone marrow, with stem cells in bone marrow, was immediately very controversial because some people were concerned that the only way to get these stem cells, these embryonic stem cells, was to destroy that IVF embryo.
Right. And that created a lot of controversy. It also actually spearheaded, I think, Proposition 71 in California that led to the establishment of CIRM, because I think the state took a strong position. The properties and potential of those cells was critical for advancing medicine in the future.
On the federal level, the first response to the Thompson and Gerhardt findings was to say that actually this research could go forward with federal funding, provided that it complied with a rule that we've had as part of federal law for more than 20 years, and that is that no federal funds can go for the creation of embryos and their destruction. And the argument was that Thompson and others, other research scientists around the world who followed using the same methods, were able in private laboratories to create these cells from donated IVF embryos. These are embryos that are created in a process in which a couple wants to have a child, cannot through normal reproduction do that, and their egg and sperm are combined in vitro, in glass, in a laboratory, and those embryos that are generated, some of them are implanted, and if a couple successfully creates a child or several children in that way, they may still have more embryos that are frozen and kept in that laboratory, and at some point they may decide they don't have any further reason to use the embryos for reproductive purposes, and they are thinking that they will discard them. And so if the people at the laboratory say to them, would you be willing to give them so they could be used for research, that is permissible. It's a private activity. There's no criminal law that prevents that. And that's where these embryos came from. So they were not generated using federal funds, but once they existed and the stem cell lines were created, the federal government said, well, we're prepared to sponsor research with them. But then in 2001, when George W. Bush became president, he called a halt to that, actually before any federal funds had been provided for research. And he changed the rules and basically said there can be no research with any newly created stem cell lines. And he said he was doing that because he didn't want to encourage scientists to destroy future embryos.
So practically speaking, that left a few hundred stem cell lines that could advance the field. And then a really spectacular discovery came in 2006 with the demonstration from Takahashi and Yamanaka in Japan that if you took a small number of regulatory factors, the sort of genes that tell cells what they should do, and introduce those into just a skin cell, you can program those cells to become a cell very like an embryo stem cell. And this meant you could make a line from anybody. If that person had a disease, then if you developed a model of that disease in the tissue culture dish, you could then have an approach to actually study the disease or find drugs that might treat the disease, something that we could never have done before.
And those cells are the often called IPS, right? They're these induced pluripotent
stem cells.
And
yes.
how do they compare, both for research purposes and treatment purposes, with cells that have been derived from embryos, the embryonic ones?
So they are in all criteria very similar, with some slight differences to the embryo stem cells. And at the moment, there are actual clinical trials going on that are comparing the properties of embryo stem cells and iPS cells.
So the result of all of this was that you had the funds here in California. There were some restrictions on what you could do federally, just the lines of approved federal stem cells. So what has come of this? I mean, what are some of the highlights that have been accomplished so far using this methodology?
Well, I would put it into two different arenas. So one of the arenas is to take the stem cells and make biomedically important cell type to be able to put back into a patient. A very good case of that is age-related macular degeneration. This is the most common form of blindness in us. About 300,000 Americans are declared legally blind every year through age-related macular degeneration. And by making this particular cell type called a retinal pigment epithelial cell and putting that back into a patient's eyes, this is now being it's being undergoing clinical trials as a potential therapy to treat age-related macular degeneration. So there's the actual use of a stem cell-derived product as a therapeutic, and it's at its early stages. Clinical trials are going on in several different areas, and I would say that many of those look promising. The second major aspect is this idea of being able to create disease models in a dish and to develop new approaches that have not been possible before to try and screen for example, drugs that might treat that particular disease model.
So rather than testing the drugs on human beings, you could just test them on the cells in the dish.
Or on animals, So for example, if we take the example of ALS, a fatal motor neuron disease, where these cells within our central nervous system die, and we have no way of getting at these cells normally. Now you can make those cell types from a patient's skin or blood sample in a dish and compare those with people who don't have the disease, and then try and design therapeutics. And this area of disease modeling and developing assays and finding new drugs is probably going to have the most rapid, largest payoff before many of these more complex approaches that involve actual cell-based therapy into the patient go through all the necessary clinical trials.
What about using stem cells to create actual organ replacements? Where does that stand?
Well, this is a very interesting area and spectacular development there in some areas. So remarkably, you can take a single stem cell from the gut, from say the intestine or the colon, and from that single cell you can engineer the gut epithelium, and then you can add back cells that are responsible for the contraction of that. And now people are adding back cells where they can actually control that the way that the nervous system does to make a three-dimensional gut architecture. The progress there has been faster than I could possibly have imagined as a scientist, and the ability to generate complex three-dimensional tissues, I think, is one of the most dramatic advances in the last several years.
And would it be possible to do it taking the cells from an individual and doing a therapeutic cloning procedure with the stem cells to derive ones which would actually match the DNA of the eventual recipient of that organ, that artificial?
So as we all know, that I can't just swap my tissues with you. We have to be matched. So this creates a problem. In principle, if we could make stem cells from each of us, we could make anything to put back into us that would be identical. There's a real significant practical problem here, and this is quality control on the process. It's very significant. So in the first iteration of this will not be the case. It will be to make products that have as wide an applicability as possible, but they're not going to be tailored exactly to you.
And would that be products that are not as subject to the immune rejection reaction?
Right, so that's where people are heading, is to try and generate stem cells that would be better tolerated in a wide variety of people, yes.
Now, what have you experienced by way of restrictions or impediments that have arisen because it remains in some ways a controversial area? Sometimes people may not even be aware of the fact that you're not using embryonic stem cells, you're using these iPS cells.
Yeah.
Have you gotten past all that because you've had the funding here in California, or are there any remaining issues that you face?
The funding in California was initially essential in getting all of this moving. Personally, I haven't suffered restrictions, but I am quite alarmed by the recent announcement of withdrawing funds or putting extra oversight on fetal research. And the reason why I find that very perturbing is that to be able to use these cells that have the potential of generating every cell type, we really have to understand how that works in real life. And unless one can understand how that works on a human to generate those different cell types, then we will not realize the full potential of those cells.
You know, we've been talking about a lot of the ways that you see hope coming out of this field. We have had the current clinical trials looking for cures, and they've moved, as you've said, really rather faster than you would have thought. There is also a concern, though, that for many members of the public, well before any of this research has proven these things, you see in the newspapers or you hear advertisements, doctors saying that for degenerative joints or this problem or that, including or potential blindness, they already have treatments. They have stem cell treatments. And this sense of enthusiasm that surrounds the work that you're doing can spill over to those situations. And some patients go and attempt that treatment, sometimes with really disastrous results. And in fact, a number of patients who got injections into their eyes for macular degeneration ended up blinded as a result. What do you think we can do about that? Is this a real problem, or are these just a few anecdotes?
Yeah, so I think there are certainly reasons for concern here. There is no regulatory oversight over these clinics that will take tissues from you and take cells out of you, culture them in a laboratory for some period of time, and then put them back into you, for example, to treat arthritis in a joint, the loss of cartilage tissue in a knee, that sort of thing. From the scientific perspective, we cannot explain how the experimental administration of those cells would work in a patient. They certainly don't replenish the tissue. Whether a patient feels some benefit of that, then there may be some benefit through some very peripheral suppression of the inflammatory system, but we can't really justify that type of work in any sort of rational scientific way. And as you said, it's open to real problems occurring if those cells get contaminated and they go into a person, as was the case in Hong Kong, I think, then somebody can really get seriously ill from this.
Mm-hmm. Well, I wonder whether the things going on here at USC are addressing the ways in which patients do so desperately want to have treatments. Are there particular things that are happening at the Broad CIRM Center that you lead that offer hope rather than just this hype to patients?
Yeah, so I think some of the most interesting work that's going on in our medical school is, for example, in the case of age-related macular degeneration. And I want to stress something that's very important about this. It's not a single school that's going to be successful in this area. It is a cross-school initiative. So some supported clinical trials that are going on for age-related macular degeneration, they involve scientists at USC. They involve engineers at Caltech. They involve doctors at the City of Hope who are generating the cells, scientists at USC and the University of Santa Barbara. It takes all of those people to come up with a good therapeutic option for patients. Right. And then there's the patients who are willing to undergo the initial test of those therapies.
Right.
So initially, a small number of people treated with these cells here in California, a small number of people being treated in Japan and in the UK, and initially some very encouraging reports from those, but it's early days.
And like all of science today, science is a team sport, and you're saying it's both interdisciplinary and international.
Absolutely, interdisciplinary, cross cities. So now I'm in a great city in Los Angeles with lots of wonderful collaborations with our sister institutions here. And as you say, and then it gets into international. So to show that a therapy is really, truly going to work, in the end, you've got to show that it works at multiple centers. It's reproducible. And that then becomes internationally collaborative at that point.
Because of the alteration of the cells in this process that you are making, in effect, a biological product, there's no question that eventually the FDA is going to be involved in oversight and approval. And I think a lot of people are surprised when we were talking before about the problems of hype, that people get told by individual doctors, I have this treatment and I'm going to do some hocus pocus here and then inject your cells back in you to cure your arthritis or whatever, that the FDA doesn't yet regulate all of those kinds of things. And the argument is that the FDA doesn't control the practice of medicine.
Yes.
The same way with a pill, that once it's approved, if your doctor wants to give it to you for an unapproved use, he or she can do so. And that's the same is true
Yes.
here. The idea being, if the cells are minimally manipulated and they're just taken out and put back, there are so-called autologous cells from the same person they're going back to, that the FDA doesn't directly regulate that.
Yeah.
It does, however, create a problem, it seems to me, for people in your field if right now, for example, there is some talk of raising private money or going back to the public here in California and asking for another bond measure to keep the momentum that has been behind the CIRM initiative. How do you differentiate what you're doing from that hype? I mean, in other words, there can be hype as to individual patients, and there can also be hype as to the public. And is there some risk that people may end up feeling, oh, this is all oversold?
Yeah. I think we have to do a very good job of making the public realize the promise without putting unreasonable expectations on what is experimental therapeutic approaches. And at the same time, we have to distinguish between what is charlatan type of approaches. So, for example, if I went into a clinic somewhere that wanted to make mesenchymal stem cells from the fat in my abdomen, how would I know they made those cells? How would I know what they had in a dish? How would I know they even put them into me? How would I know that they worked? What are all those measures? So all of those things in a proper clinical trial that's approved by the FDA, all of those things are things that you answer right up front in designing that trial, and they're all followed very closely.
I want, by the way, to encourage people who are watching to share their thoughts and to comment and indicate that they like what they're hearing or that they have thoughts about it. And we can respond as opportunity arises. The existence this coming week of the ISSCR conference here.
Yeah, that's the International Society for Stem Cell Research. This is where it's the largest meeting that brings together international researchers, and it's all coming to LA. There'll probably be around 4,000 or 5,000 researchers coming in.
What do you expect it's going to come out at that meeting? Any indications of something new and interesting that we're going to hear about?
Yeah, so the sessions that are going to deal with many of the therapeutic approaches that are undergoing trials at the moment and updates on those, all the way to the very most basic research about finding out about mechanisms of disease, mechanisms of stem cell action that in the end can be translated therapeutically.
And can you give me an example of something that might be discussed?
I'm anxiously awaiting.
Oh, I see. How about for yourself or your colleagues here?
Yeah.
What will you all be talking about? I don't want to have a spoiler for people who are sitting on the edge of their chairs when you get up to speak. But.
Well, I mentioned in my introduction that there are certain of our organ systems which frustratingly do not have their own stem cells. And the kidney, which is the system that I work on, is one of those that there is no strong evidence for a stem cell that generates multiple cell types in the kidney. And so we've been very interested in just understanding what are all the cell types, how they're generated, and trying to figure out the mechanics about how we can create all of these in a dish and use them in some useful way. I would say that we are quite behind other groups just because of the complexity of the system that we work with. It's a very complex system, second only to the brain in terms of its complexity. But the progress has been really terrific over the last 5 or 6 years.
Just out of curiosity, do you have any inkling as to why the kidney would not have stem cells to regenerate?
It's an interesting philosophical question, and I really can't come up with a very good answer to that. It's a bit of a puzzle. I can see all good reasons why it might. The only thing that I could say is that it's one of those organs that is needed critically to sustain life. And so if you damage that system, you have to repair it very quickly. And stem cell-based repair systems generally operate relatively slowly. And that might not be compatible with survival if something really acute happens. So this kidney has evolved other ways in which it can repair without stem cells. And we're studying those.
Right. Is the ability of the liver to regenerate itself an example of a stem cell-based repair?
It is thought to be an example of a stem cell-based repair system, yes.
And it's okay for that to go slower because the small part that's left of a liver can do most of the work.
Right. So if you remove a large amount of the liver, the rest of it will grow back. If you remove a large amount of the kidney, you've lost a large amount of the kidney for the rest of your life.
One of the issues that comes up in all of this area is the question of what role should the public play? Certainly, I mentioned before that during the early years of the Bush administration, there was this dramatic pullback on the willingness of the federal government to support research in this area, and that was based on values. We often think that the right way to make scientific decisions is evidence-based, and that same idea can be applied to public policy. We talk about cost-benefit analysis and so forth. But I think scientists, as uncomfortable as it may be to realize, have to know that the public, if it's supporting research, also brings values into the equation. And some of those values may be inconsistent with something which seems like a neutral choice to a scientist. And they'll say, no, this is not a neutral choice. It's one that implicates a big value, and we're not happy with that. Do you in scientific circles ever find yourself having conversations about that? And does it seem legitimate for the public to have a role in all of this?
Absolutely, yeah. And I think a great job was done in the early days before Proposition 71 here in explaining to the public and having these discussions. And currently there are a number of good organizations. America for Cures, for example, is really making a great effort to try and explain where we currently are with stem cell research, how we got here, where we're heading. So for those listeners who are interested in delving in more, I would really recommend you look at America for Cures.
Having the big stem cell meeting here in Los Angeles is a great event. Does it signal the growth of biomedical research here in the city and the region?
This is very interesting. It's a bit of a personal mission for me. When I moved from Boston, which is an epicenter of biomedical research, to Los Angeles, which is the epicenter of the media, arts, film, music, and so on. And what people don't realize is the depth and breadth of science and biomedical research that's also going on here. So I'm delighted to bring for the first time this large international meeting to Los Angeles. We've been able to bring it here with support from the Choi family and USC Stem Cell. And I'm hoping this is going to be one of many more meetings so I don't spend quite as much time on an airplane going to other places.
That's great. The opportunity to work in this area is something which brought you here with the CIRM, the original CIRM funding. Are you prepared to make the case to the public about the need to continue here uniquely in California, or especially in California, to fund this research? It does seem as though we're again at a point where the federal government is pulling back on research generally outside of, say, the military area, and to ask whether it's possible to engage the public and convince them of the value of not slowing down at this moment.
I'm definitely willing to make those arguments, and the arguments are actually very compelling about the pace of research here, and in some ways the accelerated pace of research in California has accelerated the pace of research elsewhere. So when the $3 billion of taxpayers' dollars was approved for CERN by the Proposition 71 initiative, this really galvanized the attention of many other states and countries. And what we've seen from that is the collateral growth of stem cell research in many places. And it's really early days. There's so much more to be realized. I will definitely be out there and supporting any new effort to get new funding.
And will you face any problems if the restrictions that we mentioned earlier about the research on with fetal tissue and so forth that the Trump administration has announced now, if those go forward, is this going to be something which will directly affect the ability of researchers to carry out stem cell experiments?
So we're not entirely certain what's going to happen. There's going to be another level of review that is uncertain this time until we actually go through that process. If that really does impede work with fetal tissue, it will have a marked effect. This will impede research by monies supplied by the government, by the National Institutes of Health. It will not impact research from private sources.
And or non-federal governmental sources like the CERN.
So, for example, if there was another initiative of CERN, it would be able to support that research, yes.
Right. We want to thank all of you who've been watching this broadcast on Hope, Hype, and Science. And we hope that you will like and share the broadcast. We're very grateful to the USC Annenberg School for giving us this opportunity. I'm Alex Capron from the USC Gould School of Law and the Keck School of Medicine.
And Andrew McMahon from the Eli and Edith Broad Center for Regenerative Medicine and Stem Cell Research.
Thanks for listening. Be sure to subscribe to our podcast and visit us at podcasts.usc.edu.